So, I'm going to tell you today about interprocessor interrupts. Just a funny graphics image. What it is about, this instruction writes some magic to the ICR register. The double X is the vector you're wanting to start from. That's it.
Nice though.
Actually, it's not that easy. As with virtualization, there's always some crosstalks in manuals, some details not to be missed. So let's start over. What is interprocessor interrupts all about? Is it good for you or maybe the CPU? And I'm going to do something interesting. I'm going backwards from not implementing from the start what we need to do for EP to work, then these other things that we do, what these need, and go on from there. And then I'm going to talk about some implementation details. I've made a small demo for this and what I'm going to do in the future. Interprocessor interrupts. They're just like interrupts, but actually not. When you program an interrupt controller, they send an interrupt when an exception happens, when a timer expires, etc. But with EPs you can just write to a memory address space and it is sent. It is sent through a bus to all CPUs, only yourself, the CPU that is executing the instruction. All the others, or you can specifically say which CPU you want it to be delivered to. It's related to both APIC and PIC because you need to program the interrupt controller just to use EPIC. And the advanced programmer of the interrupt controller is the one that delivers the messages. It should replace PIC altogether, but actually not, because from the second point you know you need the PIC to work, but you can hide it from working. I'm going to talk to you about a little later. And you can consider it as peer-to-peer or CPU-to-CPU. Each one has its own register to write to communicate with each other. Now's the question, why do we need EP altogether? One possibility is to just write to a shared memory space that all CPUs know about. They read it from time to time. But there's nothing wrong with IPC. You can use it, but it gets a bit short if you need timer interrupts in multi-CPU mode. And it is better just because of that. Imagine 16 CPUs. When you want all of them to access a certain memory location, you need to make some atomic operations to check that all of them access at the same time. It's all done in the background with EP supporting systems. And there's always another player, which is the CPU, that wants to gain access to the same memory location, and you get into trouble. And then there's bandwidth consideration. Try with writing to memory, or if it all happens automatically through the APIC bus, then you shave some clocks off from bandwidth, and you can use it for other tasks the CPU might do. Shared memory, actually I wrote it not to ruin the day, but it might hinder your performance. Maybe it's too rough to say ruin the day. And on EP you can rely on, that is exactly because everything is done in the hardware, in the background. You don't have to have software support to make the operations atomic. And about unwrapping, let's start from the EP. it wants someone to listen, to answer to, and here comes the first acronym, end of interrupt. Each epic interrupt needs to signal that it has done everything it needs to do, and it writes an end of interrupt into a memory mapped D word. Then there's a CPU that needs to send an interrupt. There are two players, okay, two or more. The listeners might be up to 155. And the ICR is called Interrupt Control Register. This is where you write if you want to send an interrupt. And this is purely manual. Before I talked about timer interrupts, they happen automatically. But with ICR you can manually write, for example, the booting CPU tells ICR, writes to ICR that I want to wake the other processor up, or I want to tell them that they update their cache tables, or whatever. They must have interrupts enabled, like I talked before, and now there's a case of optimal CPU mode. I even tried waking them up in 16-bit mode, but it happens, surprise, surprise, that it uses D-word access, and the memory mapped area is at the top of memory. It's around 4 gigabytes, so it's really hard to do it in 16-bit mode, so I switched to 32-bit protected mode, and the things got easier. Let's unwrap it a bit more. At the end of interrupt, I talked about it a little in the last slide. You can consider it as an interrupt controller ending. When you get the IP interrupt, start handling it, depending on what you need to do. With timers, you need to update some OS tables. And just before you make an interrupt return, you write the UI to the D word, and APIC knows that it's done with it and can send another interrupt. The interrupt point register is also written by OS, and what's interesting is that when you usually deal with programmable interrupt controllers, you have 20 or so different interrupts. With interprocessor interrupt, you just have one, and when you write to it, there needs to be someone listening on that same slot, and you need to program each CPU identically. It gets a little off topic, but with multiprocessor CPUs, you also need cache tables, the same MTRRs, everything. That's why they call it symmetrical multiprocessing. Every table needs to be identical on each CPU. Now back to topic. PIT naturally comes with PIT, which is the timer, and this gives the CPU time to breathe. You bring it to hold state and wait for another timer interrupt. And PIT hierarchy also can send an IP. This is where the automatic delivery comes into question. You program a PIT, you reroute it through APIC, and you have yourself a timer which updates every CPU in the system. There's a small, I don't know, is it a bug in Intel manuals or in my head, but I haven't got it working until now. It's possible because OSs have done it, but I couldn't make it work, so it's a bit half-baked. When you had caching and paging, it's already like an OS, but it's all sweet dreams. Okay, about all the acronyms I named before, they only one point of time need to use IDTs. They need to use GDTs. IDTs is for interrupt control, GDTs is for memory mapping, what pages to access, and of course they need to access more than one logical physical CPU. This is where we start to talk about multi-CPUs. And I think that completes the unwrapping. now we need to assemble the code. We start by usual stupid stuff. The A20 gate isn't even necessary, I don't know, but I made it anyway. Set up some segments, GDT, just before going to 32-bit, and jump to 32 or 64, whatever you choose. You need to reset the segments, program the IDT, which is very important, the pick, the pit, etc. And now gets the part of SMP. You need semaphores. It's warned in Intel manuals that if, for example, Core i7, there are 8 threads running. If the 7 other threads happen to loop the same code at the same time, bad things can happen. So I took my caution and made semaphores. When the first waking application processor finalizes what it's doing, it releases the semaphore and the next starts to do something. It's a bit longer than releasing them at the same time, of course, but it won't take more than 100 milliseconds or so. The application processors are called APs in Intel manuals, and the booting processor, or the first, is BSP bootstrap processor. And the BSP does everything to wake up the APs, and when they're all up, you can have your OS running and sharing tasks. And SMP configuration is symmetric. There are other modes, but I concentrate only on the symmetric multiprocessing. Oh, here comes the BSP. Make a fork, it's not like a separate thread, but at one place in code, there's a flag, I am a BSP. The first processor to get there, it is always the BSP. This is the flag that I have been to this code before, and there's a fork to a separate AP code, which differs from the BSP. Because BSP's task is to wait APs, we can't let it run one more time. So they take a different route and have mostly similar setup code. The APIC enabling the EP setup part, but just they don't put other processors. The first thing to do is search for the MP structure. It's a weird D-word string. But all CPUs don't have to have them. So my 2 test cases showed that one Dell laptop didn't have it anywhere in memory. I scanned all 4 gigs memory space and didn't find it. And the Core i7 I have at home tells that it has just under 1 megabyte this structure. Intel says it should be 16 bytes aligned, so it's easier to search, just every 16 bytes and 1 keyword to search for. And the MP structure references another structure that starts with PCMP. And then you can be really sure that the CPU supports multiple processors. But because some systems don't have it implemented, you can just ignore this line and go on with the initialization, enable APIC, boot up other CPUs, and just count how many CPUs woke up. If none of them woke up, then you can be sure that it's a uniprocessor system. And that's the route I took. So the MP part was in it. It worked in emulator, it worked on Core i7, but because it didn't work on this laptop, I took it out and to make it more universal. SVR is an interesting register. It's called spurious vector register. Spurious because they are the interrupts that shouldn't happen or happen only on weird cases, but it is also used for AP initialization. So you write to it the startup of the AP's code and start the sequence init zippy zippy, Intel says it needs to be made twice. The CP part, this is called when there runs startup interprocessor interrupt, which starts up the processor. Init is for just initializing. But in my tests, when I call the first CP, the AP is already up. And I read some threads that if you make a too long period between the two CPs, for example, 100 milliseconds, then the AP has already booted, set up its structures, it's already ready, and you start another CP, and it starts all over again. So sometimes it's not necessary, but Intel in its newest March version of its manual still suggests it. ICR low, it's a two-part register, that's why I call them low and high. They're 32-bit both. High bits are not used in this startup mode. In the high 32-bit part you can write the C processor that needs to get the interrupt delivered. But since I'm going to wake all the other processors, there's a 2-bit shorthand which tells wake up all processors. And I write just the ICR low part and the AP start up magically. And there's a waiting part, 200 microseconds or so, and then you count the woken CPUs and see if any of them woke up. The AP part differs a bit. Until the 4 part in 32 protected mode, it's similar, but then it jumps to its own code. It also enables APIC and increases CPU count. The BSP just writes 1 to the CPU count. The others that get to the memory just increase it. It all needs to be atomic. Because 2 increases at the same time might lose one of the increases. And then they're ready to process. I have a demo program which I can share with you on forums or USB sticks, but I'm afraid I can't show a live demo here. If anyone wants to see it, I can show them. In my demo, the BSP is the boss, because I didn't get it working in the symmetric mode where each interrupt is routed to every processor. In my demo it gets routed to only the first processor, which then dispatches the same interrupt with an IPI to other CPUs in question. About future work, the main reason why I started this is because I've long waited to make it work on Myjava, which is still uniprocessor, and I hope that my work finishes with that. The tests I've done was with one Core 2 Duo, which had 2 CPUs. They were the physical ones, and Core i7 has 8 CPUs. 4 of them are physical and the other 4 logical. They're hyper-threaded. I'm planning to bring support to other CPUs in the future. I haven't tested on any AMD system, I don't know if it even works, and test more emulators, and of course clean the code and fix some bugs, one of them being the interrupt that I haven't managed to get working this far. X2 APIC is interesting, but I think we don't really need that in the near 2 years future. It was first supported on Core i7. The older ones have either X-APIC or APIC. And if you have any questions, willing to answer.
What's new in X-APIC and X2 APIC?
They have one interesting bit disabled. It's the pending interrupt. When you send an IP, you can check the ICR if the interrupt was sent or it's still being sent. With new versions, bit is reserved, and the whole keyword is only readable for debugging reasons. You don't need that anymore. Even in my demo, I don't read it. I just assume it's sent because the interrupt handler took the interrupt handle, did send an EOI, and it's finished. You also asked before about the EP performance. I googled and I still haven't found the answer, but I hope I get it someday. The other thing, X2 APIC extends the higher dword part to full 32 bits. In the previous APIC modes, there were only 8 bits supported, so maximum of 255 CPUs. But now, logically, to 4 billion CPUs can be addressed. It's not a bit field. You write a number in the high ICR word, so you can't tell that send an interrupt to CPUs 4, 8, and 7. But you can say go with 7 and then write another later and send another EP. I don't know if it's too awkward, but usually you need to send only to all CPUs or one particular CPU.